So we have v of x here. അപ്പോൾ നമ്മൾ v dash of x എടുക്കുമ്പോൾ v dash of x will be f dash of x minus derivative of this term will be fb minus fa by b minus a. So we will get v dash of x is equal to f dash of x minus fb minus fa by b minus a. So therefore v dash of c equal to 0 gives f dash of c minus fb minus fa by b minus a equal to 0. So that implies fb minus fa by b minus a is equal to f dash of c. So hence the mean value theorem holds. So there will be at least one. So here നമ്മള് mean value theorem Rolle's theorem പറയുന്ന there is at least one c such that v dash of c is equal to 0. So there is at least one c here such that f dash of c is equal to fb minus fa by b minus a. Hence the mean value theorem is proved. So that is the proof for the mean value theorem. Now let us see a few problems using mean value theorem. So the first question is verify that the hypothesis of mean value theorem are satisfied on the given interval and find all values of c in that interval that satisfy the conclusion of the theorem. So first one is you have f of x equal to x square minus x in the interval minus 3 to 5. So since f is a polynomial, f is continuous in closed interval minus 3 pi. So it is continuous and differentiable on the entire real line, and it is differentiable in open interval minus 3 pi. So idella entire real line differentiable aanu, but that is the only requirement for the mean value theorem. So both the conditions of mean value theorem hold. So therefore by mean value theorem there exists at least one c in open interval ab such that f dash of c will be equal to fb. So that is f of 5 minus f of minus 3 by 5 minus minus 3. So that implies f dash of c will be equal to so f of 5 is 20 minus 12 varum by 8. So that is equal to 1. Now f dash of x is equal to 2x minus 1. So that implies 2c minus 1 is equal to 1. So we will have c equal to 2 by 2, so which is equal to 1. So therefore C will be equal to 1. That's the required value of C. And again let us look at another function. Okay. Second one is f of x equal to cos x in the interval pi by 2 to 3 pi by 2. So we have f is the cosine function, so f is continuous in closed interval pi by 2, 3 pi by 2. It is continuous everywhere. Cosine function is continuous everywhere, and it is differentiable in open interval pi by 2, 3 pi by 2, and we have f of pi by 2 equal to 0, f of 3 pi by 2 is equal to 0. So by mean value theorem, there is at least one C in open interval pi by 2 to 3 pi by 2 such that f dash of C is equal to fb minus fa by b minus a. So that implies f dash of C will be equal to f of, so this will be 0 by 3 pi by 2 minus pi by 2. So that is f dash of C will be minus sin C. So minus sin C equal to 0. So that implies sin C is equal to 0. So this happens when C is equal to pi. So therefore the required value of C will be equal to pi. Now we will see a few theorems which can be solved using, or which can be proved using the mean value theorem. So just write it as consequences of mean value theorem. So the first theorem we are going to prove using mean value theorem is, so that is the condition we use for checking whether a function is increasing, decreasing or constant. So if derivative is greater than 0, function is increasing, derivative is less than 0, function is decreasing, and if the derivative is equal to 0, function will be a constant. So provided it is differentiable. So this theorem can be proved using the mean value theorem. So let f be a function continuous on closed interval AB and differentiable on open interval AB. Then if f dash of x greater than 0 for every x in open interval AB, then f is increasing on closed interval AB. So this was a theorem we have seen. Similarly, if f dash of x, so if f dash of x less than 0 for every x in open interval AB, then f is decreasing on closed interval AB. And again, if f dash of x equal to 0 for every x in open interval AB, then f is constant on closed interval AB. So we will see the proof for this using mean value theorem. So let us see proof of part A. And now let x1, x2 be points in closed interval AB, such that x1 is less than x2. So let us take 2 points in the closed interval AB such that x1 is less than x2. Now our aim is to show that the function is increasing if f dash of x is greater than 0. So for increasing we must show that f of x2 is also greater than f of x1. So we need to show that f of x1 is also less than f of x2. Now, since the function satisfies, so when you have seen the theorem, you have seen the hypothesis of mean value theorem. So if is continuous in closed interval AB and differentiable in open interval AB, so therefore the mean value theorem holds in this case. Now, since the function satisfies the hypothesis of mean value theorem, so there exists, so there is at least one C in open interval x1, x2 such that so f dash of C must be equal to f of x2 minus f of x1 by x2 minus x1. So if you look at the function f, so it will satisfy this condition. So f dash of C will be equal to f of x2 minus f of x1 by x2 minus x1. So that implies f of x2 minus f of x1 will be equal to f dash of C into x2 minus x1. And now since C is in open interval AB, so by the hypothesis f dash of C is greater than 0 and x2 minus x1 is also greater than 0. So therefore on the right hand side you have both function values to be greater than 0, f dash of C greater than 0 and x2 minus x1 greater than 0 so this implies f of x2 minus f of x1 will be greater than 0. So therefore the function is increasing. And the part B can be proved in the similar way. So you start with all this. The only difference is you have f dash of C to be negative. Parts B function has a negative derivative. So ഇത് പോസിറ്റീവ് ആണ് കാരണം x1 പ്ലസ് ദാൻ x2 ആണെന്ന് മാറ്റില്ല ഇത് പോസിറ്റീവ് ആണ് ഇത് നെഗറ്റീവ് ആവും സോ ഇഫ് ദിസ് ഇസ് നെഗറ്റീവ് f of x2 minus f of x1 is going to be negative. So therefore negative ആയതുകൊണ്ട് f of x2 will be less than f of x1. So that is the condition for the function to be decreasing. And in the third case again f dash of c is equal to 0. ഈ ഇക്വേഷനിലെത്തും f dash of c equal to 0 ആണ്. f dash of c equal to 0 ആയതുകൊണ്ട് f of x2 minus f of x1 will be equal to 0. Now x2 and x1 they are any arbitrary points in that given interval. So this holds for any point x1 and x2. So therefore for any x1 and x2 f of x1 is always equal to f of x2. That means it holds for all the points x in that interval AB. So therefore the function is a constant in that case. കാരണം എല്ലാ പോയിന്റും ഫംഗ്ഷന്റെ വാല്യൂ ഈക്വൽ ആയതുകൊണ്ട് ഫംഗ്ഷൻ കോൺസ്റ്റന്റ് ആയിരിക്കും. So that is the proof for the remaining part, so that you can complete by yourself.